I would like to welcome all of you from around the nation to our Exploring the Moon Past, Present, and Future webinar. We have participants. I think I haven't updated some of those states there, but we've got quite a few states that have registered for the event, including Texas, Nevada, Maryland, Delaware, Missouri, Florida, Illinois, California, North Carolina, Georgia. I hope I didn't miss your state. Kansas as well. So we've got groups from all around the country and in grades K through 12. So welcome everyone. We're excited to have you with us. Our featured speaker, John Gruener, he is a scientist here at the NASA Johnson Space Center. We'll let him tell more about him, but we are so lucky to have him with us today, as he is a very busy individual, especially these days. So we look forward to hearing from him in just a couple of minutes. But I wanted to make sure to mention to you all about International Observe the Moon Night. That is actually an international event, events happening all around the world. As you can see in the lower part of this slide, we're showing where different events are happening across the Earth. So even though this Saturday is Observe the Moon Night, every day is a great day to observe the moon. Now, if you are looking for an event to participate in, or you want to register an event you're hosting, there's a website there, moon.nasa.gov/observe, and you can see all other things that are happening all across the nation. In any case, for us, we're going to focus on today's webinar, but we will have future ones, so you can always check our website. But today's webinar, we're going to focus on exploring the moon. And again, with John Gruener on the line, we're going to get a treat to hear about the past, present, and future of the moon. So John, with that, I'm going to unshare my slides and have you start sharing your slides so that you can introduce yourself and get started.
Good morning, everybody, or good afternoon, depending on, or possibly even good evening, depending on where you are in the world. That's something we have to do every day here at NASA, because we are working with our international partners in trying to figure out, where to go on the moon, what to do on the moon. So sometimes those early morning telecons aren't any fun, but we have to kind of rotate around the clock so that some people get to do the telecons in the middle of their workday, because it wouldn't be fair if everybody had to, always be stuck at a time slot. So today we're going to go fairly quickly through, like Paige said, this is being recorded, and you'll see all these slides and later on if you want to go back and look at them again. But just a brief reminiscence, of what we did on the moon in the past, what we're working on now, and what we hope to be doing in the near future. Particularly the year 2024 is made a lot of headlines these days, all right? This beautiful image of the moon is actually a mosaic of a bunch of individual images taken by our Lunar Reconnaissance Orbiter mission that is still in orbit around the moon. It's been there for about 10 years now. There's a camera on it that takes high resolution images. And so we've been able to make even better and better global imagery maps of the moon than what we had during the Apollo era. So we're going to have to figure out.
And you should be able to, if you're on, click on your own screen, John, you should, or use your down arrow, that should forward for you.
There we go. All right, so now we're moving. Okay, so just a little bit about me. I grew up here in Houston. I was born up in the medical center. I had an uncle that worked at NASA during the Apollo program, so that was pretty cool. And when I was in high school, I was trying to figure out what I wanted to be. I talked to my guidance counselor. And of course, nowadays they're called school counselors because I'm married to one, and they don't like being called guidance counselors anymore because they do a whole lot more than just, schedules and guidance. But my first degree was in aerospace engineering because, that sounded like something NASA would need. But as I came to work here at NASA and started work, I first started working on space shuttle missions because we were flying space shuttles back in 1986 when I graduated from college. And then we started talking about this thing called a space station, which is now the International Space Station. I did a little work on the assembly process. Every time you brought two pieces together and then the astronauts went back home in the shuttle, those pieces in space had to be a viable spacecraft with control and everything else. But what I really wanted to do is work on human and robotic missions to the moon and even Mars, because, you know, as a kid, I watched Apollo. Growing up in Texas, I love the outdoors, going camping and hiking in all of our state parks we have here in Texas and the few national parks we have. And as I started working more on the moon project and as an engineer, I needed to talk to the scientists to figure out what it is they wanted to do on the moon. Because as an engineer, you only need to design those things that are going to be used by people like scientists as they do things on the moon. And so as I talked to them and found out what they wanted to do and where they wanted to go on the moon, I found it really fascinating. So I went to night school. So I was working in the daytime as an engineer, but then I went to night school at a local University of Houston campus and wound up with a degree in planetary science. And so since 1994, I've been working on, you know, scientific aspects of the exploration of the moon and Mars ever since. So basically, you know, the story is here, if you want to be a successful scientist or a successful engineer or, you know, computer programmer or coder or whatever it is in your life, you know, get that good basic education, because, you know, once you have a good foundation of knowledge, you can flex and expand into any area that you're interested in as long as you're willing to work at it. You know, so I was married, I had 2 kids, but I was going to night school to learn planetary science. So get that good basic education. And then as you're applying that education, make sure you let your mind just go crazy and be imaginative and creative, right? Because that's what you really need in the design process. If you're designing things to do something nobody else has ever done before, it really helps to be as imaginative and as creative as possible. And then finally, you know, work hard on those things and try to make, you know, meaningful accomplishments. So, you know, we could scatter ourselves far and wide and work on all sorts of things and never really accomplish, you know, get over the goal line or make accomplishments. So you kind of have to, you know, pick what you want to do, focus on it for a while, make some accomplishments that moves you forward. And so that's what we're doing every day at NASA right now. We're trying to make accomplishments so we can actually get to the moon by 2024, because that's going to be pretty tough. That's just a few years away, as you all know. So here's a couple of pictures of me at the bottom. On the left, that's a pyroclastic flow in New Mexico, near Taos, New Mexico. In the middle, I'm standing in front of an explosive volcano called the Mare crater out in Arizona in the San Francisco field. And then on the right, just like I'm doing today with you guys, I go out and I talk to kids and teachers all the time. And this is just a picture of a girl out west of Houston in Katy, Texas. And I brought a piece of Mars. You can imagine that, because they were working on a mission to Mars, so you can see her in her spacesuit. All right, so here's our lovely moon. As Paige said, this Saturday is observed the moon night. Right now, it's a beautiful crescent moon. That's my favorite moon, little bitty thin crescent. It's hard to look at the moon when it's full because it's so bright, particularly when you're looking through a telescope. So you either have to have a filter or don't look at it too long, because it really, you know, makes your eyes hurt if you look at a full moon. Best time to look at the moon through a telescope is when it's in its either a crescent phase or gibbous phase. And then you look right along the terminator that separates night and day, and that's where you get a lot of really good relief. All right, so we're going to start off with Apollo because, you know, again, that's what got me really hooked on going to the moon. I watched the Apollo missions as I was in elementary school. Our first landing was when I was in 2nd grade. Our last landing was when I was in 5th grade. So it really impacted my life. Those astronauts were having a lot of fun doing things in a very dangerous environment, but all the engineers made sure they had the right spacesuits, the right spacecraft, the tools. I mean, you know, it's a real dance and mix between engineering and science to pull off these missions of exploration. So there I am. Right there, I'm only 4 years old. We're in the cool red tennis shoes. My uncle is the guy over on the left-hand side in the dark pants. And behind us is a big thermal vacuum chamber where NASA tested spacecraft for Apollo, where you put a spacecraft in there, you shut the door, you suck out all of the air, so there's no atmosphere in there. It's like the vacuum of space. And you can also change the temperatures to make it really, really cold, or you can shine some heat lamps on it like the sun and make your spacecraft really, really hot, all right? So even at a young age, like I said, I was fascinated by this space program. All right, and this kind of sums up this quote from Arthur C. Clarke. Now, you know, a lot of people think of him as a science fiction writer, and if you ever have to read science fiction in school for a project, I would highly recommend some of Arthur C. Clarke's short stories. But in the early 50s, a lot of what he was writing was just telling how things are going to happen in the space program someday, and a lot of them have come true. So, you know, if you go back to what he wrote in 1951, there's a book called The Exploration of Space. So telecommunications satellites, space shuttles going up and down, space stations in orbit, visits to the moon, all those things he talked about in the 50s have actually happened. You know, we haven't settled down on the moon and lived and worked there for long periods of time, and we haven't made it to Mars yet with people, but we will someday. I mean, even back then he knew, you know, this was hundreds of years in the making to do all these things. And the text that's in the black pretty much summarizes my engineering career. All right, a technical problem, it's really challenging, but we can do it, right? But there's no point in going to the planets and to the moon unless we do something when we get there. And that's all about my scientific career. You know, scientists have things they want to do on the moon, places they want to sample. They want to measure the moonquakes. They want to understand the environment, particularly at the poles of the moon, where now we see evidence of water ice, right? So again, here's another interplay between the black text, which is the engineering, and the red text, which is science. And he was saying all these things way back in the 1950s, and they're still true today. All right, so again, our Apollo missions when I was in elementary school from 1969 to 1972. I know that seems like a long time ago. I'm about 5 or 6 years away from retirement, but we have a lot of young people working here at NASA that we're mentoring, and we're getting them ready for the return to the moon, because people have called my generation the Apollo generation. And the next generation, including you guys, are the Artemis generation. You can participate in this program called Artemis that we'll talk about, you know, in a few minutes, and get us back to the moon, get us to Mars. And so, you know, back in the Apollo days, we were on the moon 6 times, and we brought back about 840 pounds of different rocks and soils. We landed at 6 different locations, and it was just like, you know, opening up a whole new field of science, because we hadn't had any real samples from a you know, planet yet. And so this was just really cool times. And we not only learned about the moon, but we were learning a lot about the inner solar system and how the planets Mercury, Venus, Earth, Mars, and the moon, of course, how they form, because all these inner solar system bodies formed in a similar way, you know, at a similar time. And so the moon is basically a very small planet. It went through the same stages that the larger, you know, planets did, but it's just in orbit around the Earth. So of course it's called, you know, a moon or a satellite. And we won't get into the whole Pluto situation, but because it was once a planet. But so, you know, a lot of times we focus on the surface of the moon, but up in orbit, there was an astronaut flying in the command module. So that's the little gumdrop shaped spacecraft in the upper right corner, the little, you know, it's actually pointing down towards the moon. But this picture shows you all the science instruments that were on side of the command module. And in the lower left, you can see that as this service command module flew over the moon, the science instruments were mapping the moon. All right. But those little swaths of data that you see is all we got. So you can see over on the left-hand side where it says near side, there's an area of red surrounded by yellow and then green. And you kind of get the idea from those swaths that something's going on there, because we don't see it anywhere else on the moon, right? But this was it. This is the kind of data that scientists had to work on to try to understand the moon at the time. All right, so other than those samples back from the moon, we also have over 300 meteorites that have been picked up in Antarctica, in some of the dry deserts like North Africa on the moon. And, you know, the challenge of meteorites is once you've determined they've come from the moon, you know, comparing them to the rocks that we brought back from the moon, we don't really know where they came from on the moon. All we know is they came from the moon, right? But some of these meteorites are so different than the Apollo rocks we started to get an idea that maybe our knowledge of the moon wasn't complete, that there are plenty of other areas that are a lot more diverse than where we landed with our Apollo astronauts. So these lunar meteorites, which just keep falling on the Earth, I mean, we keep finding new ones every year, are really expanding our knowledge on what the moon is made of and how it varies over its entire surface. All right. So here's the, the one slide will summarize what we learned from meteorites and the Apollo missions. I'll try to keep it in 30 seconds, but the moon is very old. All right. It's about 4.5 billion years old. And since it's been out there in the solar system, it's been battered and smashed by comets and asteroids, and little, anything from dust-sized particle to something, as big as a house, bigger than a skyscraper, even, some things smashed into the moon that were probably the size of small towns. And so all of this battering, of course, breaks up the rocks on the moon. And so there's a very, the whole moon is covered or blanketed by a loose surface material. Here on Earth, we just call it dirt or soil. But on the moon and on planets, we call this stuff regolith. So regolith is a fun term to throw out there that nobody understands. But basically, it's the dirt on the moon. And when we look up at the moon at night, when you look up at the moon on Saturday, you'll see dark areas and bright areas. And the dark areas were smoother. We knew that. We looked through telescopes. And what scientists, then deduced from the smooth nature of the moon, the dark areas of the moon, was they were younger than the bright areas of the moon, because very simply, they had fewer craters. So if you have a brand new surface, like a lava flow, coming out and resurfacing parts of the moon, it hasn't had enough time for things to smash into it and make craters. So there's a very simple relationship between very young surfaces with very few craters and very old surfaces with a lot of craters. So you can do this in your classroom. You just get a map of the moon, pick out, start counting craters, and you get an idea of the relative ages of the moon. And so these dark areas of the moon were much younger because we age dated them. So now we have ideas, but they're still billions of years old. Not, we haven't found any lavas 4.5 billion years old, but certainly lava's 3 billion years in that time frame. And they're very similar to the lava that comes out of the volcanoes in Hawaii, or the lavas that cover our ocean floors. This stuff is called basalt, and basalt is the most common rock in the inner solar system. There's basalt on Mercury, Venus, Earth, Mars, our moon. So it's very, very common. So it shouldn't have surprised us that those dark areas were basalt. Long time ago, people like Galileo thought maybe they were seas. Just like we have dark seas on the Earth, they thought maybe those were seas on the moon. So they called them Mare. That's a Latin word for seas. The bright areas of the moon turned out to be much older, just like we thought by counting craters, but now we age dated the rocks in the labs, and they truly were much older, and not so much basaltic in nature, but very feldspar-rich rock. So if you guys in science class are learning things like Mohs scale of hardness, you'll recognize that term feldspar because it's a very hard igneous rock. I think it's about 9 or so on the Mohs scale. So that's kind of it in a nutshell. What the moon is made of and its very old geologic nature. Now, the near side is what we see. So over on the left, that's the moon we see every night. We can't see the far side because as the moon goes around the Earth, it's spinning on its own axis, just like the Earth spins on its axis and we have day and night. The moon also spins on its axis and it has day and night as well, right? But the way the moon is set up is as it's spinning on its axis, it's also going around the Earth, and we always see the same side. Maybe some of you guys have already learned this. So we have the near side that we see, we have the far side that we don't see from Earth. And matter of fact, no explorers were there until just last year when the Chinese landed their Chang'e 4 mission on the far side, kind of in the lower. So if you look at the far side, and that's kind of the face of a clock, where 12 is up high, 6 is down at the bottom. You can see a dark area there between 6 and 5. That's where the Chinese landed in this really big crater called South Pole Lake and Basin. So that's kind of what we see when we look up at night. But this is what geologists like to do. We love to color, right? And so we look at the moon. Again, we count craters. if there's a brand new crater and it splashes out material called a crater ray, and that material lands on older material, we now get an idea of which is older and which is younger through another very simple principle called superposition, where the old stuff was there and then something new happens, and that new landform is sitting on top of the old landform, so we know relatively what is younger and what is older. And so that's basically what you're looking at here, a geologic map of the moon, where the browns are the oldest parts of the moon, the yellows are the youngest parts of the moon, and the youngest parts could be, you know, a few 100 million years old. But remember, look on the left, all that red area, those are the basaltic lava flows. You know, those are even 2 and 3 billion years old. So the moon is very, very old, but it's still getting hit by stuff, and, you know, hence the yellow, young, fresh craters, you know, a couple 100 million years old, and maybe even younger. We'll talk about that in a minute. All right, so here's where we landed on the moon. And I see, Paige, this is our first question. So our Apollo missions were very successful. All right, we haven't been back on the moon since 1972. So your question is, do you think the United States should send astronauts back to the moon? And if yes, what do you think we should be doing there? And if we shouldn't go back to the moon, why not? So
All right.
Go ahead, Paige.
Oh, yeah. So now we want to sort of get some ideas from you in the chat window. So what do you think? John talked about our missions to the moon. He's showing their landing sites here. Should we send astronauts back? And if so, why? Or if not, why not? Okay. So we're getting some answers from Downs. They said, yes, we should go back because we can find new things we didn't know. Urteria Elementary says, yes, explore the far side of the moon. Down Elementary also says we have better technology. San Benito High School says yes, so we can continue to learn more about the moon. Murfreesboro Middle School says yes, absolutely, to learn more about the moon with better tools. Garnet Elementary definitely thinks we should go back. And even Reconnect to Nature says, yes, let's go. We need to use it to get beyond to other worlds. Sneed's Ferry Homeschool also says we should go back to the moon to learn what more might be there. So I'm hearing mostly yeses, including GTTEA says yes, and exploring maybe that far side. We don't refer to it as the dark side, it's the far side. And even Mann Elementary says yes to study new rocks and explore more. We've got to go back. Yeah, so we've got a positive crowd.
So these kids are a lot smarter than a lot of people in the world, because some people will say, well, the moon, we've been there, we've done that. We don't need to go back. All right, so let's just spend real quick to dispel that myth. So here's a picture of the moon with our 6 landing sites that NASA went to the moon. Again, I always say we, but I was in elementary school. So when NASA went to the moon, this is where we landed. I think you guys understand the story of Apollo 13, and it didn't quite make it to the moon, but they did get back safely. So look at the geometry. So look at the distances kind of between these areas and the angles, you know, because we're going to do a little geometry problem here. So real quickly, the moon is much smaller than the Earth, all right? If the Earth was a 6-inch cantaloupe, so do this, go to your produce, you know, section in your local grocery store, get a 6-inch cantaloupe. Well, then the moon itself would be 1.5 inches line. So now you have a good representation right in your hands of the Earth and the moon. And at that scale, you would separate them by about 15 feet. And now you have the Earth-Moon system right in your classroom or in your kitchen at home. And of course, the moon goes around the Earth, all right? But there's no water covering the surface of the moon. So it turns out there's as much surface area, exposed surface area for exploration and settlement someday as North and South America, or, you know, 90% of North and South America. So, you know, look at the globe in your classroom, maybe erase Florida, you know, maybe erase all the little knobs and pieces that kind of stick off on the end. Most of North and South America is what we're talking about in the idea of surface area that's available on the moon. All right, so I'm going to remind you of where we've been. And what I'm going to do is I'm going to take the distances between these landing sites and the angles, the geometry, you know, you go up northwest or southeast between landing sites, and I'm going to apply these to North and South America. And I'll show you how much we would know about North and South America. There it is. All right. So Apollo 16 would be right here in Houston at the Johnson Space Center. And you can see with the same distances and geometry involved, the farthest west we would have landed with people would be Apollo 12, kind of out around El Paso. And the farthest north, I heard Paige say that we have people from Kansas in this webinar today. The farthest north we would have been with people would be right in the middle, around Salinas, Kansas. And then east, Memphis, Tennessee, where Elvis was, right? So that's your knowledge of North and South America. What could we talk about or know about the Appalachian Mountains? You know, over on the East Coast there on the right side of the picture. Not a whole lot because we didn't land there. How about the Rocky Mountains? Again, not a whole lot because we didn't land there. Some of these mountains with little holes on top in Washington and Oregon and California, where smoke comes out of these mountains, and now we know they're volcanoes, right? We wouldn't know about those. And of course, you might have learned that a lot of those volcanoes along our western coast, and then all along Mexico and South America, those are because of plate tectonics. As the ocean plate dives down underneath the continental plate and volcanoes form. Plate tectonics is so critical to understand the Earth. And yet, if these were the only places we landed on North and South America, we wouldn't have a clue about plate tectonics. And if you don't like geology, but you love biology, think about all the biological diversity you would miss if these were your only samples. You know, the Olympia Peninsula in Washington State is just beautiful. The Everglades in Florida, the swamps in Georgia and Louisiana, very biodiverse areas. And then, you know, we haven't even touched South America. So that Amazon rainforest, probably the most diverse region on the earth. You wouldn't have a clue about that biodiversity. So, you know, have we been to the moon? Yes. Have we done the moon? No way. And you guys all saw that in your answers back to me. So here's another question. Robot technology has come a long way since the Apollo missions. Do you think the United States should send robots or robotic spacecraft to the moon before the astronauts, along with the astronauts, or we don't really need to send robots at all, we'll just send people back?
All right, so in that chat window, we want an A, B, or C in there, but we also want you to explain your answer. The best part of science is not just coming up with an answer, it's being able to explain it. So Downs Elementary says most of the students there say send before the astronauts go to the moon. And maybe we'll have some additional input coming in as to why they think that might be important. And so Garnet Elementary, our group from Kansas, they said B, with the astronauts, because we need astronauts to check on the robots. Murfreesboro says B, so they can observe different parts of the moon, so with the astronauts. SSA, our solar system ambassador from Florida, says send astronauts since the robotic probes are limiting. So I'm sure we have some discussion going on in there, and robotic spacecraft could be with them on the surface or maybe in orbit, so don't limit your view of what robots could be. Now, your Tria Elementary says with the astronauts to aid in data collection. Sneed's Ferry Homeschool says with the astronauts to help build, and possibly they can go farther than them to see other areas of the moon that they perhaps can't get to. GTTA says, you know, to send them with the astronauts or before the astronauts because it could be dangerous for humans. Ben Bright Elementary says with the astronauts because we believe astronauts and robots should be used so they can explore areas and gather information faster. So the large majority say send them with them. What do you think, John?
Well, those are good answers. And maybe we, next time we do a webinar like this, we actually put a D and say both A and B, because that's what we're doing. Robots are great trailblazers, and we're getting ready to talk about robots. But, you know, the people can't do everything once they get there. So the kids talked about the people repairing robots, which is great because they're going to wear down and break. Maybe we want to change the science instruments that are on the robots as they go to different places. So we use the same mobility capability or mobility chassis of the robot, but we change out different science instruments depending on what it is we're doing. So robots are going to be very important. And I look at robots as an exploration bargain, all right? We have a lot of equations here at NASA, but luckily the most important equation is really easy, right? And that's mass equals money, right? We couldn't do the space program without money. And if you want to send mass to the moon, if you want to send a lot of mass with people, you better have a lot of money. Robots are a lot smaller. Smaller mass means smaller budgets and smaller amounts of money to get those robots to the moon. Here's a picture of the Lunar Prospector spacecraft that went into orbit around the moon in 1998. You can see a human technician working on it. See, those robots don't require air, food, and water, right? So that just makes the human spacecraft even more massive and more expensive. The robots, we don't have to bring back home to their families because they don't really have families, right? I know some people get real attached to their robots and kind of kid, yeah, I'm the father of that robot or I'm the mother of that robot. But really, these robots don't have families to come home to, right? And so it costs money to bring things back to the Earth, right? So robots are very helpful in accumulating data for us, but then also working with people. I noticed one of the schools talked about dangerous areas. Yeah, we don't want to send our people in the dangerous areas. Like we're going to talk about in a minute, the poles of the moon. It's very, very cold in some craters that never see sunlight. Can't send people in there because it's too cold, but we can send our robots in there. So they're a great partner with us in our explorations. And what a lot of people don't realize is that 13 robots actually beat Neil Armstrong to the moon. Our first mission, Ranger missions, you know, they were purposely built to slam into the moon. That long tubey thing on the upper left is a camera, almost like a telescope. And as you got closer and closer to the surface, the pictures got better and better and better, right? But you see 6 of them were unsuccessful. Only 3 of those worked. Then we had lunar orbiter missions that stayed in orbit around the moon with their cameras and took pictures of potential landing sites for the Apollo astronauts. And all 5 of those worked, so that was great. And then surveyors at the bottom, they actually landed on the moon and showed that the moon's surface was hard enough that we could actually stand on it and walk on it. Because at the time, some people thought that the moon was just a layer of dust. And when you landed on the moon, you would just sink into the dust. And then you couldn't get off again. So that was pretty, you know, a serious thing we had to figure out because we sure didn't want to send our Apollo astronauts to the moon and have them sink into the dust. So 5 successful surveyor missions, they showed that we could land on the moon. It was solid and people could walk on the moon. And of course, the moon has its own gravity. So you're not going to float off the moon. Once you land on the moon, you're going to stay on the moon. You can walk on the moon. If you drop something on the moon, it will fall to the moon, right? There's a very cool video out there of Apollo 15 where they dropped a hammer and a feather and they both fell to the moon. I'm not going to tell you what happened, but maybe you guys can go watch that video. All right, so starting in 1994, so if you remember, 1972 was the last time humans walked on the moon. Well, there was about a 20-year gap where nobody was exploring the moon, all right? I should say the Soviet Union did have some robotic missions up till 1975, all right? So not quite a 20-year gap if you include the Soviet missions, but you know, a long time went, but then we started going back to the moon. And in the US, Clementine was our first mission in 94. I talked about Prospector, but look, all those other missions, and I can see I need to update my chart here to put Chang'e 4 mission on here because they landed just last year. So a lot of robotic missions to the moon, some in orbit, some down to the surface like the China Chang'e 3 mission at the bottom, all right? I don't know if you've been watching the news, but recently an Israeli company tried to land on the moon, but that didn't quite work out. Then the Indian Space Agency tried to land the Chandrayaan-2 Vikram lander. That didn't work out, but we're still trying, all right? And we're going to talk about that in a minute, all the people that are trying. The beauty of these missions, remember those little swaths across the moon from the Apollo days with the Apollo astronauts, because we stayed near the equator on the front side. We put these robots in polar orbits that go over the North Pole and over the South Pole, over and over again. And then the moon rotates underneath. And so we get new swaths of data every time the robot spacecraft go over. So now, instead of those little, you know, swaths like we had in Apollo, we have complete global data sets from the North Pole to the South Pole. that we can count on and learn more about the moon because of this renaissance of robotic exploration. So I do have this chart in here, Chang'e 4. Here are pictures from the far side of the moon. With the Chinese mission landed this January of this year, and that little rover, U2, is driving around. And so these spacecraft have lasted, they're working on their 9th lunar day. So where they are, you have 14 Earth days, 14 days of sunlight, followed by 14 days of darkness, and it gets really, really cold. So that's a real challenge, is trying to get your robotic spacecraft to survive the lunar night. But the Chinese have figured it out, and they're very successful. And now they're into their 9th lunar day, and that little rover is still driving around. So it's a very successful mission. All right. Here are future missions that are in the books. You know, the United States, and here at NASA in the upper left, we are trying a track where we don't send NASA spacecraft to the moon. We buy commercial services to the moon. So I work at NASA, and sometimes I have to go to NASA headquarters in Washington, D.C. Well, I don't fly on a NASA airplane, and I don't stay in a NASA hotel, and I don't eat at NASA cafeterias. I do all of that commercially, right? And so I buy a ticket on, say, Southwest Airlines or United Airlines, and I stay in a Hilton or a Marriott once I get there. That's what we're trying to push here in our country, is to set up a commercial lunar delivery capability, not only for robotic missions, but even human missions, so that someday humans could fly to the moon on, say, a Boeing spacecraft or a Lockheed spacecraft or a SpaceX spacecraft, right? The other countries in the world aren't there yet. Their national space agencies are building and owning all of the missions themselves. But you can see there are quite a few countries all planning, or, like China, that are on the moon right now. A lot of different nations working to go to the moon, different places, different reasons, different types of rovers. So it's very exciting times. Here are some of those companies I talked about with you that are working with us for commercial robot missions. Blue Moon Lander. So you maybe never heard of Blue Moon, but you have heard of Amazon. So Jeff Bezos, the owner of Amazon, has a space company called Blue Origin. And Blue Origin is designing the Blue Moon Lander to deliver things to the moon, just like Amazon delivers stuff to people all over the earth, right? Astrobotic from Pennsylvania, Moon Express in Florida, Maston Space Systems. These are only 4 of the 9 companies that we're working with to get delivery systems to the moon in the near term. And our earliest missions will be in 2021, right? Or maybe 2020, 2021. Astrobotic hopes to land on the moon in 2021. All right, so there's the moon. We've been talking about them for a while. What I call the new moon are places we haven't been to, or things we don't quite understand. We're getting ready to talk about the poles, because that's where we're focused on for 2024. But the far side of the moon, some of the kids said we need to go to the far side. I wholly agree, because a huge, again, think of North and South America. Half of that hasn't really been explored on the surface by anything except for Chang'e 4 and the Chinese. So the far side is wide open territory. And then the underground. Now, we're not going to talk a lot about the underground, but we think there are caves on the moon. We see these holes that are what we call skylights in the lava portions of the moon. And here on the Earth, in Hawaii and other places that have basaltic lava, a lot of times these things called lava tubes form, right? We think there are lava tubes on the moon. We now have evidence that there are skylights going down into something below the moon. But of course, the skylight goes straight down. We don't know how far the lava tubes go. So that'd be kind of fun for you guys to get on the internet and learn about lava tubes. And maybe some of you could even go into lava tubes in your local areas, because we think there might be on the moon. And some people think that might be a great place to live, to get out of the extreme temperatures on the moon. Remember, the moon's constantly being pelted. That's why we have all those craters. Well, your habitats, your houses on the moon are also going to be pelted by things. So maybe you live in caves to protect you from all that. And so that'd be kind of funny, well, ironic maybe, that, humankind used to live in caves, right? We all see movies and read about cavemen, right? Well, maybe our first people on the moon are going to live in caves, and we're going to start all over just, on the moon, just like we did here on the Earth. So those are the three areas that I call the new moon. All right. The far side, again, you know, it's different from the near side. Look at the bottom picture where you see the purplish pink colors. The front side of the moon is on the left, and you see a lot of greens and yellows. That's the lava flows and stuff, and this thing called creep that I don't have time to talk about, but scientifically it's interesting. And then look at the far side. You know, they're different. And so we're trying to understand that difference between the near side and the far side, and how that played into, you know, where the moon formed, how the moon formed, why the moon formed. Why do we have these two different two far side, near side? Why are they so different? We don't know, but we would like to figure out. All right, so here's my one image on the caves of the moon. These are some of the three of the holes that we've seen on the moon. And in the little cartoon in the lower left, you get an idea of what we're thinking it might be like, where our spacecraft is looking down the hole, but there is a cave that we can't really look into, but we can see, you know, just under the underhang, if you will. And so we know that you can go in about 10 meters or so underneath the actual hole that we can see. But we don't know if it extends even further than that, because these lava tubes on the moon could be very, very long, have lots of volume to set up places to live and work and be out of that extreme environment of the moon. Now, the challenge of that, of course, if you're going to live underground and you're doing all your exploration and work on the surface of the moon, you're going to have to go up and down quite a bit, right? So the caves on the moon don't answer all of our problems, but maybe, who knows, someday. They may just be tourist attractions, because I love going in caves. Here's a picture of the lavas on the moon. The blues and purples are really old. So if you look at the ages down below, the purples are 4 billion years old. The youngest are about 1 billion years old. But these are models. We don't know. The only stuff we've sampled are the lunar meteorites. We don't know where they came from, or the Apollo missions. And so we know those few areas. So we have to model this, but more missions to the moon will help us understand the volcanic history of the moon. These really weird things called irregular Mare patches. Remember I talked a long time, Galileo called these dark areas Mare, or seas. So he kept that word Mare, but look at these weird blobby looking things. We have no idea what they are. We think they're very young volcanic features, and maybe even younger than 100 million years old. We're gonna have to land there with robots or with people to try to figure them out, but they're really cool. So we call them IMPs. We love our acronyms at NASA, but that's another neat thing you might look up on the internet if you're looking for a project in your science class, these irregular Mare patches, because we have no idea what's going on there. All right, and of course, unfortunately, last summer, before maybe about a year and a half now, they had the largest eruption on Hawaii. Many neighborhoods were covered with lava. Sometimes in those eruptions on Hawaii, you see the big orange fire fountain in the upper right. Well, we found little orange and black beads at Apollo 17 landing site. And so we know that there's this type of volcanic eruption on the moon. All those little red triangles in the lower right is where the locations of all these volcanic ash deposits are. So, again, very limited in where we went with Apollo, so much more to learn about the moon as an entire planetary body in the future. All right, so this is what's really driving us now, water ice on the moon. And all these little green freckles are where we've detected water ice on the surface of the moon near the North Pole on the left, the South Pole on the right. And the reason they can exist is because they're inside craters that never see sunlight. I think we're going to have a chart here in a little bit that will explain that geometry, but this is really something. Just like in the deserts of our world, oases are so important, right? Because of the water. These are like oases on the moon. In the lunar desert, Buzz Aldrin called it magnificent desolation, right? And that's really, there's nothing there. So, that's kind of a good name for it. But all these little freckles are possible oases where we could get water ice and then melt the water ice and purify it and drink it. We can also split, water's H2O. I think a lot of you guys know that. Split the hydrogen from the oxygen. Now we have rocket propellants. So water ice on the moon is going to be so important. All right, so we just talked about, the moon and all the different things that are out there. So here's a question. What do you think would be the most valuable resource on the moon, and why? So we talk science, but a lot of science is finding resources and then humans using those resources to live off of, right? So from this very quick description of potential resources that I talked about, what do you guys think are the most valuable resources?
So let's see what we'll find in the chat window. And again, that why is really important. So from Downs Elementary, right away, they jumped in and said water ice, because it will help people survive on the moon. San Benito High School says water, because it's a resource for all living things. Garnet Elementary also says water, because it has H2O in it. Randall Middle School says water to make fuel from that H2O. Reconnect to Nature also says water for survival. Aerospace Academy, our group from Mexico, also agrees water. Sneed's Ferry Homeschool says water and food, because you can make fuel, and of course food is important to be able to survive. Downs Elementary also adds in that water could be used for rocket fuel. So water seems to be it. Now, one of our solar system ambassadors also says potentially helium. Also, we have water for survival from Bembright Elementary, Utria Elementary, and even Murfreesboro. So,
well, that's all. Yeah, that's also the consensus of all the space agencies that are talking about going back to the moon. That exactly. Water is that critical resource, right? And so we're all focused on the poles right now, but we don't know a lot about this water, right? It's in some places, but not others. How deep is it? Our knowledge of water only goes down, about half a meter. What is it like 5 meters below the surface? Are we going to find real solid ice 5 meters below in the pole? We don't know. So we're going to have to go there with people and robots, right? And of course, water, everything on life depends on water. Not only us living, but industry uses water quite a bit. So it's going to be just as important in space. We just talked about life support and rocket propellants, but water is going to be just as important in space. And so that's why a lot of folks are focusing on the poles of the moon. All right. So here's a question for you guys. Now, I kind of let the cat out of the bag earlier in the talk, but when might we send people back to the moon? Because here it is, 2019, and nobody's on the moon, just the one Chang'e 4 Chinese robot.
And so, yeah, you might have let the cat out of the bag, but we'll see how many were listening closely. So already Frank Long Elementary, Sneed's Ferry Homeschool, Downs Elementary, San Benito High School, Murfreesboro Middle School, Garnet Elementary, Reconnect to Nature, every single one of them is saying 2024. And even
Great.
Randall Middle School says 5 to 10 years, which would be within our 2024. So
yeah, well, that's what we're shooting for. Will we make it? We're not going to send people to the moon unless we're technologically ready and it's safe to get them to the moon. But we're shooting for those mid-20s. 2024 is the date Vice President Mike Pence and the National Space Council put out there for us to really challenge us. But that's where we're working towards, all right? So we're calling this program Artemis. And it's to send the first woman to the moon, because all the Apollo astronauts were men, right? And then a man. We're looking at 2 people to the surface of the moon in 2024, right? But hopefully what we learn from our robotic missions to the polar regions, what we learned from the people missions to the polar regions, is how to use that water in a sustainable way. Space is very expensive. Remember I said mass equals money. Well, if we don't have to bring so much mass up to the moon because we're using the local resources and natural materials there, we just saved ourselves a lot of money, right? But we got to learn how to do this. And it's going to be a long process, many, many decades, probably even centuries of expansion and learning how to work on the moon. But we're going to try to start it in 2024. Here's a little artist's conception of what it might be like at the poles. The Earth will always be low on the horizon at the polar regions. And that's because, so here's kind of a geometry lesson. Our Earth, it spins on its axis, That axis is tilted about 23.5 degrees, so we have seasons. Thankfully for us people in the northern hemisphere, we're not pointing at the sun anymore, so our temperatures are getting cooler. Well, the moon's axis of rotation is only 1.5 degrees, all right? And so the sunlight at the equator comes in straight, overhead. At the poles, it just skims the surface. And so the sun's going to be on the horizon. The Earth itself is going to be on the horizon. And this little image on the left is kind of an illumination map of the South Pole. So where you see brightness, that means like 80% or maybe 90% of the time is lit by the sun, and the complete dark is where the sun never shines. And then the shades of gray are kind of in between. So it's important for us to understand where the sunlight is, because we're going to be using solar arrays, just like we do here on the Earth, to generate electricity for all of our activities there. All right, so the main goal of all of this is learning how to work and live on another planet. The moon's only like 4 or 5 days away by rocket travel, so it's really close. So if things go wrong, we can come home. But, not just going there, like the Apollo missions, as great as they were like camping trips. 3 days on the moon was the maximum they did in Apollo. And so what we want to do is go there and stay, learn how to work and live, and then everything we learn, kind of use the moon as a proving ground. Everything we learn, we can apply to other planetary surfaces like Mars, right? But we learn it first on our proving ground, the moon. And a big part of that is going to be using the natural resources, so we don't have to bring everything from Earth because it's expensive. And sometimes our rockets blow up on the launch pads. And if you're waiting for that grocery delivery from the Earth and your rocket blows up, what are you going to do, right? You're on the moon. So we're going to learn how to live off the land. We're going to learn how to use those materials. Somebody mentioned growing food. That's been one of the things I've worked on here for most of the 1990s. I called myself a space farmer because we are learning how, or thinking about how we would use the soils on the moon and Mars to grow plants. Whatever isn't there as far as nutrients, we bring with us in slow release fertilizers. And then we can use our life support systems to help regenerate some of the human waste and plant waste back in the soil. So living off the land is going to be so important. And then, like I said, using the moon as a proving ground for the rest of the inner solar system, right? Everything we do on the moon, we can apply to other places like asteroids and Mars. Probably not Venus, way too hot. Probably not Mercury, way too close to the sun. But asteroids and Mars are our near-term targets, probably within our lifetimes. So I hope you guys had fun. Here's my attempt at talking like Yoda from Star Wars, right? Close, interesting, and useful, the moon is, right? And it's patiently waiting for us. It's always there, 3, 4, 5 days away. We just have to get there with our people and robots. So that's it, Paige. I hope everybody hung in there. I know that was a long presentation, and we have about 5 minutes, I believe.
Yep, we've got about 5 minutes. So John, if you actually want to stop sharing your screen or stop sharing, then we'll just see you. Now, first of all, even though we only have about 6 minutes or so, you gave us so much information and so many great things to think about. So thank you so much. And you have to depart at the top of the hour. Is that correct?
Yeah, I have a few minutes I can go over, but yeah, I have another meeting I have to get to because, as a matter of fact, I'm working on a team where we're trying to model computer-wise with code, try to model the water distribution in the polar regions. So, something on my laptop just pulled up. I have my lunar water instrument measuring sub-team meeting in 5 minutes, but I can be a few minutes late. But sure, right. Let's hit some questions.
All right. So one of the gals from De Zavala Middle School asked, how long does it take to get to the moon? And you briefly answered that at the end, but can you tell us again, how long does it take?
So if you went straight from the Earth, directly to the surface of the moon, it takes about 3 to 5 days. But that's if you have really big rockets like we did in Apollo. If you use smaller rockets, you have to be a little more clever with how you travel out there. And some of these robotic missions take up to 30 days or even longer to get to the moon. So it just, it's just like here on the Earth. You can get from California to New York in an airplane, in a matter of hours. But you can't afford an airplane and you have a car, you can get across the country in a matter of days, right? So it's the same way, depending on how big your rocket is, how much money you have for that mass you're trying to send out there. It can be anywhere from 3 to 5 days all the way up to 30 days, trips to the moon.
Awesome. So great question, and thank you for that answer. So we had another question actually from GTTA, one of our groups in Texas, and you talked a lot about lava, and they're wondering, well, how did this lava get there? Does the moon have a core? Can you talk a little about that?
Yeah, so if you remember, I said the moon formed very much like the inner planets of our solar system. So yeah, the moon went through a differentiation. So, that basically means that the denser materials sank to the middle of the moon and formed a core. I mean, the moon has a core, a mantle, and a crust, just like the Earth does. But the moon doesn't have any plate tectonics. It's just a single, plate, if you will, the crust. So underneath the moon, all those radioactive elements, as they're decaying, they generate heat. All that stuff coming together to make the moon also generated heat. So there was a lot of heat trapped inside of the moon. And of course, that heat is hot enough to melt rocks. And so just like on the Earth, you have magma and it finds its way to the surface and then, spills out to make lava flows. So yeah, the moon did differentiate just like our Earth. And there is a core of the moon, a mantle of the moon, and a crust of the moon.
Awesome. And so those comparisons are quite interesting. And the moon rocks really help us understand that as well. Downs Elementary, they want to know, one of their students is asking why the far side of the moon has, is it older rocks than the near side? Why is it so different, even photographically, which another group asked about?
Right. And the most obvious answer is we don't know, right? So we can measure, or we can count the number of craters and see that it looks older than the front side. And we can eventually get rocks back from the far side and age date them. And we're going to confirm that it's very old. But why the far side is pelted more than the near side really goes to all that lava, all those fresh, young surfaces on the near side haven't been around long enough to get a lot of craters. So now the question is, well, why isn't there lava on the far side of the moon? We don't know. We don't have a clue. We do know from our orbiting spacecraft, there's one called GRAIL. You can look up GRAIL, that's its acronym. It showed that the crust on the far side of the moon is thicker than the crust on the near side of the moon. Why? We don't know. But maybe that thicker crust is harder for lava to get through, or magma to get through, to come out on the surface as lava. So we think it has something to do with the thicker crust on the far side of the moon, but we have no idea why the far side of the moon has thicker crust. Is it because the moon was tidally locked, so the near side of the moon always saw heat from the Earth? Is it because of the gravity? So we just don't know. So all of those things are hypotheses and theories and models. And we won't answer those questions till we actually get there and make measurements. But yeah, awesome. that baffles us, why the near side and the far side are so different.
And that's such a great thing about science. It's almost like the more you learn and the more you see and the more you observe and find out, the more questions that arise. That's a great part of science. So here's another question from Mann Elementary. They're wondering, how long do you think people will be able to stay on the moon?
Well, number one, that determines on how long all the governments in the world want to keep paying for people to stay on the moon. It takes money to have those people up there. Back in the Apollo days, NASA set up a series of seismometers on the moon, and we were measuring moonquakes. And after about 5 years, somebody who was in charge of the money decided, well, we need to turn those seismometers off because it's costing money, right? Well, they did. And so we only have about 5 years of a good seismic understanding of the moon, which is sad because, you could live in California for 5 years and not really experience an earthquake and say, oh, there are no earthquakes in California. But we all know that's not right. Yeah. So it really depends on how long the governments want to keep funding this. But also those commercial partners I was talking about, those commercial partners will only go to the moon and stay on the moon if they can make money doing that. So there's going to have to be a market developed on the moon. Probably that market is going to develop around the natural resources of the moon, just like it does here on the Earth. You know, we have a lot of companies that make lots of money on gas and oil and selling electricity and selling gold. So, you know, the natural resources on the moon will probably drive some markets. So as long as there's a market demand on the moon and private companies are making money delivering people to the moon or housing people on the moon, then we'll stay there. I think once we get there, humanity will stay there, you know, for a long, long time. But it's going to be touchy at the very beginning, and it's probably not going to go as fast as we'd all like to, all right? But it's all just, you know, will and grit. You know, how much grit do we have to stay there? How much political will? How much market or economic will do we have to stay there? Because the moon is a long-term investment. Don't think you're going to make money right away, right? If you're in the commercial world, the moon is a long-term investment. So hopefully we stay there. You know, once we go back, we stay there for a long, long time.
And that kind of addresses one of the questions from our GTTEA group that was even thinking about tours to the moon. And it's all about market and money, and if you can get there, and what kind of availability that is.
Yeah, later this year or maybe next year, some of these companies like Virgin Galactic or Blue Origin are going to be flying people up into space. And, you know, it'll be a 15-minute joyride, you know, or an amusement park, but you're going to go up into space, you're going to stay there for a few minutes, and then you're going to come back down. That's going to start happening within the year. People are going to fly into space commercially. You know, the problem is it's very expensive. Right now, you know, it's a couple $100,000 for somebody to go up into space with one of these new companies, right? But the price will come down as we get better and better capabilities. So yeah, it's all about the market, you know, and people willing to spend their money to go to the moon.
Awesome. Now it is a couple of minutes past the top of the hour. So
how about one more question?
Okay, so for the groups, we'll ask this one question from Randall Middle School because they have a question, and it's really kind of a little bit about you. Okay. When are you thinking about retiring? And if you ever do, which we don't want you to, but if you ever do, what are you going to do with yourself? Anything that would still be space related? Can you share a little bit about that?
Sure. Yeah. So I'm 58 years old right now. And, you know, most people retire in their early 60s. So that's kind of what I'm thinking. Now, I will not retire if we're really on the moon with robots and people, right? And 2022 comes along and we're really going to be on the moon in 2024 with people. There's no way I'm going to retire because it's going to be so exciting. But if the plan gets pushed out a little bit and the schedule gets pushed out a little bit, I'll retire because, you know, none of us are guaranteed tomorrow, right? So you got to live every day like it's your last day. Now you can't do crazy things because you got to prepare for the future, but you have to have fun every day. And live life every day because none of us are guaranteed tomorrow. And so when I retire, will I stay in the space program? Again, working as a consultant or a partner, maybe doing these kind of things with schools. It will really depend on how things are going. You know, for actively exploring the moon, you bet. But I have hobbies. I like history, so I do a lot of genealogy research to understand my family history. I like painting miniature soldiers. Historical miniature soldiers, and then conducting war games, miniature war games on tables. I said earlier, I love the outdoors, so I love camping, hiking, exploring, fishing, hunting. So there's never, I can never spend too much time outdoors. And so, you know, those are the kinds of things that I'll do in my retired life. I'm also a tuba player. I hope some of you guys are in band. I love band. I think it expands your mind playing musical instruments. And I still play tuba, even at 58. So hopefully I'll still be playing tuba and doing all of my hobbies once I do get out of the space program.
Awesome. And that's such a great question to end on because as you all can see, you know, the passion for space exploration that John has, it's catchy. And it's something that drives you to even want to work longer, even if you were thinking about retiring. But John, as busy as he is and as many hobbies as he does, I think he'll always be doing something active with people, with his family, and perhaps even with students like you again in the future.
Yeah, well, that's so important to talk to you guys today, because people like me are going to eventually retire, and we're going to need people like you to come up behind us, to be those engineers, those scientists, those computer programmers. You know, we even have lawyers here at NASA because we're working with commercial partners. So there's a lot of legal documents. We have educators like Paige and Suzanne working at NASA. So we have a whole slew of careers that you can work on at NASA. And we really need you guys, some of you guys, to, you know, come in and join the space program. So guys like me and the younger gals like Paige and Suzanne can retire someday. So I hope I've inspired some of you to think about it, at least, because I love this job. Every day I learn something new. And you know, what a great life when you can come work on really cool, exciting, difficult things and yet learn something every single day.
Absolutely.
So I got to run to my telecon so we can talk about measuring water at the poles in my real work life.
Well, thank you so much, John. You know, if you can live it, you can dream it. If you can dream it, you can live it. And John is certainly can attest to that. So thank you, John, for all your time. Thank you to all the students out there. John, if you've got to disconnect, we totally understand. So we appreciate all your time and energy.
Okay, well, we'll see you guys later.
Awesome. And for those of you, as John is disconnecting here, we so appreciate your time. We certainly hope that you've learned a lot from John. You know, if you can love what you do, you never work a day in your life. And so, you know, John's running to another meeting here, and I'm sure many of you have to run off to your next classes or so, but we so appreciate your time in joining us today. We hope you learned a lot. We'll look at some of your questions, see if I can email you some of your responses if we didn't get to them, and we hope you enjoyed connecting with us today. So with that, we'll officially bring this to a close. Thank you again for attending, and teachers, I'll send out a message about the archive as well as a little survey so we can get some feedback from you. So thank you again, everyone. Have a great rest of your day and a great semester. Don't forget, International Observe the Moon Night is this Saturday. And every day you can look up and see our beautiful moon. Thanks for joining us. Have a great day.